Yeah.
Okay.
All right, guys. So then our next speaker is Sara Lapenta from the University of Salerno. Sara is an assistant professor there that recently started, yeah, from what I understand. And she's going to be speaking to us about a logical algebraic point of view on random variance. So please, Sara, the floor is all yours. Gonna go.
Thank you. I love to have a typo in the first slide, but whatever. Okay, thank you for being here, and like a full disclosure, there will be actually no logic in this talk. This is a algebraic semantics talk, so I'm gonna talk about logics, but from the algebraic semantics perspective. So somebody in the first row here is very happy. So sorry for that. You might like somehow get the gist of the logic I want to go to. So a logical algebraic point of view of random variables. What I mean by that. So the idea is, this is a project I've been following for the past 4 years, more or less. And the idea is to kind of define a meta-mathematics of probability, in some sense, some kind of universal algebra approach to probability. And in order to do that, I moved like with attempts for a while, and then I landed on a, I don't want to say very nice, but on a like well-behaved infinitary logic system whose algebraic semantics seems to do the job very well. But before going into the details of this, I just want to tell the story of how you can do probability in non-classical logic, and also why somehow you feel the need to do that. And this comes back to actually a series of lectures by Giancarlo Rota, in particular the Fubini lectures he was giving in Italy in 1998, in which in each lecture he discussed one problem in probability that no one likes to bring it up. And in particular, in the first lecture, so this is the reference for the collector of these 12 lectures. In particular, the first problem he brings up is that a revision of the notion of a sample space is it was Rota's ultimate concern. What he means by that? Well, he means that pointless probability, meaning point-free probability, deals with an abstract Boolean sigma algebra and a real valued function defined on the sigma algebra, which imitates the definition of probability. The problem is to define an algebra of random variables. And the setup is not as artificial as it may appear. Among probabilists, mention of sample points in an argument has always been bad form. A fully probabilistic argument must be pointless. What was his point here is that when you do probability, when you actually work in probability and you work with random variables and you apply probability, you never use your sample space. What's important is mostly where you land with your random variables. And in that perspective, it was, and you actually use random variables, like the main object of studying of probability are random variables rather than the sample space and the probabilities you are dealing with. So according to Rota, it would be much more efficient to develop a mathematical settings in which you can have as points random variables rather than the sample space. So this was his point of view. And there is also another point of view which hints in the same direction, and it is Nelson's point of view, according to which you can do probability, you can do some kind of algebras of random variable, but in order to do that, you need to have addition and multiplication. So you need algebraic structures in which you can at least discuss summation and multiplication, maybe multiplication by scalar numbers, because you need to do convex combinations, and these are all the things that you actually need in probability. But actually, at some point in his lectures, Rota didn't want to pay homage to Her Imperial Majesty, the theory of commutative ring. So how can we have structures that are universal algebraic, but they are not commutative rings. So this was more or less the point. So can we have a metamathematics of probability in which your primitive objects are random variables, but you don't take the structure of a ring, you take something different, something which has more the flavor of or what you have in mind. And well, by the end of this talk, I will have a proposal for this, maybe not the perfect one, but at least it's not commutative rings. So they will be both happy, Nelson and Rota, with this, I can assume, because it will have multiplication and sum, but they will not be commutative rings, so yay. Well, but first of all, before going into discussion and before making this proposal, I want to make another point, and it is which type of probability measure we are going to discuss, because of course we want an algebra in which the primitive objects are random variables, but in order to talk about random variables, we need to talk about probability. So which probability? You will see by the end that I will work with algebras that are the algebraic semantics of a logic based on Lukasiewicz logic. And in that respect, you can do probability in a subjective manner. What do I mean by that? Like De Finetti approach to probability. Bruno De Finetti based his notion of probability on the notion of coherence. So let's take a step back and talk about coherence first. So what is coherence according to De Finetti? Well, imagine to have two players, a bookmaker and a gambler, and they are just wagering money on certain events of interest. In De Finetti's setting, an event, like a probabilistic event, is anything you are willing to bet money on, and this very simple fact comes with some restraints. For example, events are stuff that we can check if they happen or not. Like I cannot bet on in 500 years aliens will invade the Earth because I have no way to check if my bet was successful or not. And also with this notion of event, we have to agree on what means, like, okay, if we are betting on tomorrow it's gonna rain in Brisbane, we have to agree on what it's gonna rain means, like just a shiver, like it has just few drops of rain, a thunderstorm. What do we mean by it's gonna rain? So this very simple fact, betting on something we are interested in, comes with a baggage of restriction for the notion of an event, but we are not going to discuss it here. And anyway, assume you are betting money. A system of bets is coherent if there is no way for the bookmaker to incur in a sure loss, meaning that there is no way for the gambler to arrange the stakes in the bet in order that she wins money independently on the events involved in the bet. So this is a very somehow simple and coherent definition of coherence, right? I mean, a book is coherent if the bookmaker is not always going to lose money. Otherwise, because the bookmaker is the one that decides the books, like the odds you are gonna play on, and they are incoherent if the bookmaker is giving an assignment that makes him lose money in any possible circumstances. So more formally, with this definition of coherence, let's take it in classical logic. So an event, now I can think of it as a formula in classical logic because it is something I can express in natural language, and I will somehow translate it using classical logic. And assume we have n formulas, so n different events. We are betting on these n events. And the bookmaker publishes a book, meaning that he assigns to each formula a value inside the unit interval 0, 1. And the gambler now chooses the stakes. So the gambler is choosing the amount of money he's gonna put on each event. Notice that they are taken in the real. So theoretically, the gambler could put a negative amount of money on an event. This means that this game of betting we are doing is somehow reversible, because if the gambler puts a negative amount of money, gambler and bookmaker are switching roles. So this is called reversibility. And anyway, the gambler chooses the stakes and pays this amount of money to the bookmaker. Now, we have to check what happens here. Let's assume that we can think of a possible state in the world in which the events happen, some of them do not happen, as Boolean evaluation of formulas. So every word is just a Boolean evaluation, a possible evaluation of my formulas. And then in every possible word V, so for any evaluation, the bookmaker pays to the gambler 0 if the formula is false in that word, and 1 is the formula is true in that word. And so the total balance from the point of view of the bookmaker is this thing here. So the money he got from the gambler minus the money he gave back to the gambler. So sorry, he pays, this should not be 1, but should be sigma I, like 1 times sigma I to be precise. And so this is the total balance of the bet. Now, in this setting, according to what I said before, meaning that a book is coherent if there is no way for the gambler to incur, for the bookmaker, sorry, to incur in a sure loss, coherence just means that for any choice of the sigma i's, there is a word V in which the total balance is greater or equal than 0. So the bookmaker is not losing money in any possible word once the gambler has made his decision on the stakes. Is it clear so far? Okay. Okay, now, how this relates to probability, because so far there is no probability here. There is a game and it is a betting game. Well, you can define probability on Boolean algebra in the very standard way, meaning that a probability on a Boolean algebra is just a functional which is normalized, meaning that it sends the top element of the Boolean algebra into 1, and it is additive on disjoint events. This is something quite normal to do. Notice that this is just additive, not sigma additive. And the power of the Finetti setting is that the notion of coherence comes exactly to having a probability function in this sense. So if you have so you can generalize this. We discussed this for formulas. You can do it for every element in every Boolean algebra, taking evaluation in that Boolean algebra. Given a Boolean algebra and a set of events, any book is coherent if and only if there exists a probability function that extends that book. So essentially, a book is coherent if it is partially somehow a probability measure, and it can be extended to a full probability measure in the whole Boolean algebra. And this is a very powerful result by Bruno De Finetti, because of course it gives a subjective definition of probability, like of Kolmogorov probability, because subjective because the probability is just the amount of money I'm willing to bet on something in a way. So in this sense, it is subjective. And now, coming back to the original question by Giancarlo Rota, in this framework, there is already an answer to that question, because by stone duality, every Boolean algebra is an algebra of continuous and 0-1 valued functions, meaning random variables, because continuous functions are definitely random variables, defined over a topological space, which is the spectral space of the Boolean algebra. So I write here max A, but it is the ultrafilters of the Boolean algebra. And also there is a way to connect Boolean algebra with sister algebras by the Stone-Gelfand duality. And this gives also that ring theoretic structure that Nelson wanted for random variables. And furthermore, via the Finetti's theorem, there is a algebraic definition of probability, because it's just a functional, so it's something that we can understand algebraically. The problem is that with just this setting, there is a very strong limitation, because you can only discuss very specific random variable, which are continuous functions that take value in 0, 1, like 0, 1, not the unit interval. And the topological space on which you are considering your random variables, it's a very peculiar space, because it's the space of ultrafilters, and we know it is a totally disconnected compact and Hausdorff space. And this leaves out way too many spaces that are of interest for people in probability. So of course, the point here is that we would like at least to draw totally disconnected, because compact and Hausdorff is something that people in probability use. And also we would like to draw continuous here, because it's too strong of a requirement. We know we just need measurability to talk about random variables. So how can we do this? Well, dropping totally disconnected was done by Daniele Mundici using MV algebras. Now, what are MV algebras? I assume very few of you know what an MV algebra is, right? Yeah, like 2 people in the room, probably. Yeah, okay. I'm not gonna give you the axioms, because you will forget it as soon as I move on with the slides. So don't worry, I'm just gonna give you an intuition. So MV algebras are the algebraic counterpart of Lukasiewicz logic. So Lukasiewicz logic is an infinite valued logic that somehow generalizes classical logic by essentially dropping the law of excluded middle. And it's the algebraic counterpart in the sense that just as Boolean algebra has the semantics of classical logic, MV algebras are the algebraic semantics of Lukasiewicz logic. But they can also be looked at as unit interval of lattice ordered groups for people familiar with more algebraic notions. And they are, in general, a generalization of Boolean algebras. So any MV algebra becomes a Boolean algebra when the operation you have on the MV algebra is idempotent. So they are a generalization in this sense. So how do we build MV algebras according to this idea? What does it mean, unit interval of lattice ordered groups? So consider 0, 1, the unit interval of the real numbers. So the real numbers are a group, of course we know that. They are lattice ordered because they are totally ordered. So it is a lattice ordered group, although it's much more than that. And you can define on this unit interval this operation. So this is a truncated sum. So it is just the sum of the 2 numbers until the sum is inside 0, 1. If it goes outside 1, you just cut it to 1. And this is the negation, meaning it is the complement of the element to 1. And then you just take 0 and 1 as constant. You can just take 0 actually for the purpose of this. And then NV algebras are the variety generated by 0, 1 in this language. And this is the only definition you will get. So essentially it means that they are the algebra that satisfies the same equation as does 0, 1 with these operations. I'm not gonna give you much more than this because you don't actually need it. You will see very soon that the only NV algebra we are gonna need is this one. So take 0, 1 with these operations, and that's the only algebra we are gonna use because it generates the variety, so we can do a lot with that, at least in this setting. This is this one is exactly the way you build any NV algebra, because this is much stronger than what I said. This is something like any NV algebra comes from a lattice ordered group exactly in this way. So if I have a lattice ordered group with an element which I call strong order unit, and I do the exact procedure here, putting the strong order unit, I get any possible NV algebra. So if you are more familiar with groups and lattice ordered structure, you can think of it in that way. Otherwise, just keep in mind 0, 1 with these operations. What's nice is that you can do probability on NV algebras. You have the notion of state. So a state of an NV algebra, just as a side note, they are called state because the definition comes from quantum logic. It's just a name. It does not mean states in any modal logic way you can think of states. They are just called like that. And it's just an operator on the NV algebra, which is normalized, meaning it sends the top element of the algebra into the top element. What I didn't say, sorry, any NV algebra is lattice ordered. So it's a bounded lattice, distributive bounded lattice, and then it has all the other properties. So I always have a top element and I have a lattice order. And then the other equation, this one, is very similar to the one I had before for Boolean algebras. I just use the truncated sum instead of the join. And instead of the meet here, I have the Morgan dual of the sum. So my primitive operation in this sense, instead of taking join and meet, I take the truncated sum and it's the Morgan dual in this sense. So these are gonna be like a strong disjunction and a strong conjunction. And Daniele Mundici defined this notion of states, and he proved many nice properties for states that I'm not gonna go into the detail of that. There is just, and also many other people worked on states on NV algebras. This is a very, developed subject. Like this list is very not complete by any means. These are just the paper I'm more familiar with, but it's a non-complete and non-exhaustive list of people that have worked on states on NV algebras. But there is one result I want to mention for states, and I'm gonna give it in a very specific framework. So as I said before, we are not gonna need any strange NV algebra. There are some strange ones though. We only gonna need one class, which is very nice and very well behaved, and it is the class of semi-simple NV algebras. So semi-simple, it's in the sense of universal algebras. So it is just a subdirect product of simple. But when you do this with NV algebras, it's equivalent to say that there exists a compact and Hausdorff space, topological space, such that A is a subalgebra of the algebra of all continuous functions from X to 0, 1. 0, 1, the NV algebra unit interval 0, 1. So that's why I said you don't need the whole structure. Just know that we will always think of NV algebras in this talk as algebras of functions. for now, the semi-simple will be continuous function on a compact Hausdorff space. So this is the main point here. And there is a very famous theorem, which is an integral representation proved independently by Thomas Krupa and Giovanni Panti, that says that if I take any state of a semi-simple MV algebra, there exists a Borel regular probability measure such that the state is just an integral. So it is at the expected value of the random variable f, if I think of the continuous function as a random variable. So the probability is actually the expected value of this random variable. What does it mean, Borel regular probability measure? Means that the measure here is defined on the sigma algebra of Borelian subsets of X. Borelian is the sigma algebra generated by the open of X. Oh, a lot of topology, sorry. I like topology. I like measure theory. That's the problem here. I should have put a disclaimer. There will be a lot of measure theory in this talk. But this is interesting. I mean, you can get the feeling of what I'm saying. I mean, the point is that this very algebraic definition, which is two axioms in a very algebraic settings, are integrals. I mean, it's very beautiful, right? I mean, I have two very basic axioms in a setting which is universal algebraic semantics of non-classical logic, and then I have continuous functions and integrals with a universal algebraic object. So it's really a powerful setting, the one we are working in. Yeah. And this space X, just to give it a bit of a concrete feeling, is the set of maximal ideals. Just like in Boolean algebra, you take ultra filters, and they give you a totally disconnected compact Hausdorff space. If you take maximal ideals in an MV algebra, here the definition of ideals is usual, downward closed subset, close to the sum, the truncated sum. And maximal ideals in MV algebra can be topologized in the usual way, exactly with the same definition you get a topology on ultrafilters. And they are compact and Hausdorff topological space. And what's also very important for the setting I'm using is that, again, you can have a coherence criterion for states in the same way you have it for probability in the Boolean setting. So if you take any MV algebra and you take a finite number of events, here you can take formulas in Lukasiewicz logic if you want. It's going to be the same idea. Then a book, which is an assignment, is an n tuple of numbers in 0, 1, is coherent if for any choices of the stakes there exists a homomorphism. So I have replaced evaluation of formulas with homomorphisms in the same way you do with classical logic, such that this total balance is greater or equal than 0. So it is exactly the same definition as before, but this time, this H of AI is not 0 or 1, is any real number between 0 and 1, because I am evaluating into MV algebra. So my truth values are not 0 and 1, are infinite. There is an infinite number of truth values here. And again, you have the coherence criterion that says that if you have an MV algebra and all of these definitions I gave before, a book is coherent if and only if it can be extended to a state on the algebra. So states are a very simple two-equation definition in universal algebraic settings, but they give you probability measures. Actually, they give you Borel regular probability measures by the Krupa-Panti theorem, and they allow you to think about the elements of a semi-simple MV algebra as random variables. And this was actually the answer that Daniele Mundici gave to Giancarlo's Rota problem, because this is exactly what we said so far. So, and this is just a rephrasing of the Krupa-Panti integral representation. But for any Kolmogorov probability space on a point set sigma and Borel sigma algebra of, sorry, this is an omega, right? Omega and Borel sigma algebra on omega and any probability measure which is regular, there is an MV algebra and a state such that the probability space can be constructed starting from the MV algebra. This is essentially says that semi-simple MV algebra are algebras of continuous random variable on a compact and Hausdorff topological space. And again, this is a solution for Giancarlo's Rota problem, because it says that if I am in the setting of MV algebras, semi-simple MV algebras are exactly the algebras of all continuous random variable. But again, continuous random variable, we would like to go beyond continuity and stick to just measurable functions, which is gonna be, it will be better, right? So I lost track of time. How much time do I have?
So we started at 12, so we can go.
Okay. So how do we go now beyond continuity and to just measurability? We need to do another little leap here. So we had MV algebras that we just said algebras of continuous functions. Well, on algebras of continuous functions, you can do something very normal. So you can multiply each function by a real number. So if I have the function x plus 2, I can have 2/3 x plus 2, like I can multiply by real numbers, so like in a vector space. And then I can do countable suprema. They will not gonna be all the time continuous countable suprema of continuous functions, but you can then definitely do these operations. Okay, now take this out of continuous functions and just imagine an algebraic structure in which you have all the language of MV algebras, so the O plus, the negation, the constant. You add the possibility to multiply by scalar real numbers, essentially, and to do countable suprema. So, for example, so this is when I will say later RIS MV algebra, I'm gonna mean MV algebra in which I can multiply by real numbers. So for example, if I take the algebra of all continuous functions, not just a subalgebra, but if I take all continuous functions from a topological space with some properties, topological properties, then this thing here is exactly an algebra in this class, which I didn't mention earlier. I'm gonna write RMV sigma to mean MV algebras in which we have a scalar multiplication and a countable suprema. But again, you don't need to remember all this very technical thing, because we are gonna always use this very simple type of algebras. So we are gonna take algebras of continuous functions, algebra of 0, 1 real function, not continuous, from any x, not topological space, but any set x to 0, 1. So in particular, which is closed under pointwise countable suprema. So in particular, if I take bounded measurable functions from x to 0, 1, they are an algebra, or they form an algebra of my type with the operation of MV algebras, because they are close to countable suprema. I can multiply any measurable function by a scalar, but I'm gonna take scalars between 0 and 1. Otherwise, I will go outside of 0, 1 for my codomain. And I will call these things RIS tribes. I don't know why they are called this. I mean, they were already called like this in literature when I start studying them. I don't understand very much the name. So let's call it race tribes, but the main object of my setting are this set of bounded measurable functions from x to 0, 1. 0, 1, unit interval, 0, 1. Okay, now, I already said algebras a few times, but you might argue, but these are not algebras. We have a countable suprema. What algebras are you talking about? Well, they are algebras. They are infinitary algebras. And there is a whole theory of infinitary universal algebra. I'm like, you can find reference, for example, in, I don't know, a long paper or a short book by Slonimsky. It's a 100 pages book. And there are all the basics of infinitary universal algebras. The point is that the countable suprema can be thought of as an operation of countablearity, which makes this class a class of algebras in this language. So we have the truncated sum, the negation, the zero, the countable suprema, and then one operation for each real number between 0 and 1. So this is a very big language. But this makes things a lot easier because I can now use all the power of universal algebra. And in particular, the risk tribes I mentioned before, they are SP of 0, 1, where S and P are the universal algebraic operators, so subalgebras of products of 0, 1. Of course, taken in this language. So they are also preserving the countable join. And what's even nicer is that actually any other sigma complete Rissenvi algebra, so every other algebra in this class of algebras is actually a homomorphic image of a tribe, so SP of 0, 1. And this allows you to handle them a little bit easier. And what's even nicer is that they are a variety, not just a class. They are the variety generated by 0, 1 as a infinitary algebra in this language. And this was like really the starting point of this project, because having a class of infinitary algebras, which seems rather complicated, but then it's just generated by the unit interval 0, 1, allows you to do a lot of things. For example, allows you to say that since it's a variety, free algebras exist. And exist for any number of generators. So of course, in order to get a little bit of intuition about, sorry, just pause for a second. Spoiler, spoiler, something inside of here will be the algebras of random variable I want. So of course, having this in mind, it was very important to characterize free algebras here. So to have a sense of how the canonical algebra, the standard algebra in that variety is, in order to understand if they are a good candidate for the algebra of random variables. And it turned out that actually they are, because the free algebras are the most used algebras of functions in probability, because for any number of generators, they are algebra of bare measurable functions. What does it mean, bare measurables? I will drop this second 0, 1 in a while.
Sorry,
Yeah.
One quick question for the previous slide. So, infinitary algebra here, you mean some kind of version of Kirchhoff's theorem where the equations are going to involve infinitary terms?
Yes, exactly. So you allow for infinitary connective, and yeah, this is actually I don't have the axiomatization. I just proved that it was HSP of 0,1 using the Loomis-Sikorsky theorem. So we first proved this theorem and then this, but there is a paper by Marco Abbadini in which he has an axiomatization for a different type of structure, and you can recover it, and it should be finite axiomatization, but the infinitary terms, exactly. So these are, so the free algebra is very nice. It's an algebra of measurable functions, of like well-known improbability measurable functions. What's a bare function? Just to be complete. There are at least 3 non-equivalent definitions of bare functions, but in this case, for like this domain and this codomain, they all collapse on the same thing, luckily for me. This is the definition. So you take a topological space, a bare subset is just an element of the sigma algebra generated by the 0 set of the continuous function. So you take all the points of X over which a continuous function is 0. You do this for every continuous function. You generate a sigma algebra with them. And in this way, you get bare, the sigma algebra of bare subsets of X. And then a function is bare measurable if, as usual, it is measurable with respect to these sigma algebras. So the preimage of a bare set is a bare set. But this might seem a bit obscure still. In the finitely generated case, the description is even nicer because it's just Borel functions. And this was a very good find because we are aiming to have probability measures, and we just said that the free algebra in our potential variety in which we will find random variable, it is the algebra of Borel functions. So it's really going in the direction of what you need to do probability. And this is compatible with what I said before, because when you work on a hypercube of with k at most countable, Borel and bare subsets are the same. So just to give you an idea, because this seems very obscure. So from a algebraic setting, we got free algebras, and these free algebras have a very strange shape. How do you get this result? I'm not gonna give you a proof. I'm gonna give you some drawing. Don't worry. So let's call in this way the free algebra. One inclusion is very easy to do. So you get the projection of the coordinate-wise projection is a Borel measurable function. This you can find in any book. And then this is the algebra generated by the projection. This is very easy to prove. And then you get one inclusion. The other inclusion, it's a little bit tricky. The idea is that by some very standard arguments that involve the shape of these functions, it's enough for us to prove that the characteristic function of any Borel subset is a term in the language, can be written as a term in the language. And the idea to do that is to prove that you can do this for half-open intervals because they generate the sigma algebra of Borel subsets. And again, the idea is that these functions here, they are these piecewise linear functions. It's very well known for people that work in the setting of MV algebras. Those are terms in the logic. They can be written as terms in the logic all the piecewise linear functions between 0 and 1 can be written as terms in the logic. And then what do you do? To get the characteristic function of R1, you just take these, sorry, if I do this from home, they're not gonna see me. So you just take these piecewise linear functions and you make these like the slope steeper and steeper, like, yeah, you wanna make it more vertical. So you keep doing this. At some point, your join is gonna break the continuity and is gonna give you exactly what you want, meaning the characteristic function of the half open interval. And since each of the FM here is a term in the language, the join of them is gonna be, sorry, the meet of them is gonna be a term in the language. And this is the way you get Borel measurable functions starting from, sorry, this is the way you get every Borel measurable function as a term and vice versa. And if this was not enough measure theory for you, I have more. No, because now we have this very big class, but of course it's a nice class because you have the possibility to actually include measurable functions in your algebraic setting. I mean, this says that I can take a Borel measurable function and I can write it as a term in a class of algebras. I can write it as a formula in logic, in an infinitary logic, but still, this means that I can take a Borel function and it's possible to make it into a formula in some logic, in a logic in which I have to be able to have countable join and meet, but it's still a logic. And this is something very powerful if you want to try to do like a meta-mathematics of probability. But this is the whole class is a bit too much to do that. We have to restrict a bit, and in particular, we will restrict to this subclass. So we just do ISP of 0, 1. So this means that we are going to restrict to those algebras that are subalgebras of 0, 1 to the x for some x, wherever x, non-empty x. And you can characterize this algebraically. For the one interested, this means that these algebras are the one in which the intersection of all maximal ideals that are closed under countable suprema is trivial. This mimics the definition of semisimple. That's why I call it sigma semisimple. And again, by a very nice categorical equivalence we proved, these algebras, so having an algebra here, having an algebra that satisfies this condition, it's the same to say in the countably generated case that there is a subset of the hypercube such that A is the algebra of restriction of Borel measurable function to that V. And this is a very concrete point of view. So that's why this is the class of algebras you want, because you want concrete measurable functions. And this is saying that every algebra which is sigma semisimple, which is in ISP of 0, 1, it is the restriction of Borel measurable functions to some V. This V is not any random V. It has to be, in particular, an intersection of Borel sets, not just countable, any intersection. But you can take a Borel subset itself. You can take the whole hypercube. You can take a G delta set, which has the countable intersection of opens. And all of these are going to give you nice properties. But now, how we are going to use this class? The idea is that now, if you take any set B and you take any sigma algebra, calligraphic B on B, you take the algebra of measurable functions from B to 0, 1, and you endow 0, 1 with the Borel subsets of 0, 1. This is always gonna be a sigma semi-simple algebra, but vice versa, any algebra in my infinitary variety is isomorphic to an algebra of this type, if and only if it is sigma semi-simple. So this is the answer essentially to Giancarlo Rota's problem, another partial answer, but it says that sigma semi-simple algebras, which are an object in an infinitary variety of algebras, although a bit complicated, but not really that much if you are more familiar with it, are exactly algebras of measurable functions from any measurable space. Your restriction is gonna be only your codomain because you need 0, 1 there. But this is a restriction you are gonna have with any non-classical logic. I mean, you cannot it's very hard to put something different from 0, 1 if you want to do it with a fuzzy logic. It's like your usual, like the prototypical algebra, the standard algebra, the generic algebra also is very often gonna be 0, 1. So you can try to tweak it, but this is not such a strong restriction, right? Because mathematical fuzzy logic somehow calls for 0, 1 as a set of values. And this is more or less what I said, but of course we have to add an ingredient because this is almost the answer to Rota's problem, because here I'm just talking about measurable functions. In order to have random variables, we also need a probability. And to have a probability, we have to have a state. But instead of a state, since we are in a setting in which we are doing countable suprema, we also want states that preserve countable suprema. So if you add a state that preserves countable suprema, and for every probability space, the algebra of all random variables from this space to 0, 1 is a sigma semi-simple algebra. And vice versa, for any sigma semi-simple algebra with a sigma state, there is a probability space such that the algebra is isomorphic to an algebra of measurable functions. And this is more properly the answer, one answer to Giancarlo Rota's problem, because it says, you can do algebras of random variable. You have to put yourself in this infinitary variety and select a subclass. But it's not just any subclass, it's just ESP of 0, 1. So it's the pre-variety generated by 0, 1. And there is literature on pre-varieties of algebras. So it's not some very random object, some very random subclass we picked. So everything came like around very nicely, if I say so myself, of course. But I mean, I am advertising this, so come on, guys, this is very interesting, right? Even though you don't know any measure theory. Sorry. I wasn't sure about the audience, so I tried to balance a bit of more philosophical notions with a bit of more mathematical notions. Maybe too much mathematics. Disclaimer, another disclaimer, I am a mathematician, not a philosopher, so as you can probably tell by the slides here. Of course, we can, sorry, coming back serious for a moment. We can also take it to another level, because actually the very first thing we did with this setting was to, instead of just trying to solve Rota's problem and say, okay, this is the algebra of random variables, we tried first to obtain a non-classical notion of random variables. So what's going to be a non-classical random variable or a generalized random variable? Yeah, indeed. Okay, and this is done in this paper. There should be a recap of the references at the end. Actually, this is the first one appearing, right? I think I removed almost all of them. What's a generalized random variable in our setting? it's just a homomorphism in the variety, in the infinitary variety that depends on K. So we call this a K-dimensional observable, and we use the term observable because in the literature of MV algebras, the attempt to do algebraic counterparts of random variables were always called observables. And again, it comes from notion in quantum logic. But I would like, it's better described if I say generalized random variable. But a K-dimensional generalized random variable is just an homomorphism from the free algebra into A. And we do this only in the countable case. It can be done in general, but it's easier to describe this in the countable case with a countable number of generators. And in which sense they are generalized random variable? In the sense that if I take any measurable function given as a tuple of measurable functions from x to 0, 1, this induces a generalized random variable in this way. So you send, since this is the free algebra, you send the generators into the corresponding f in the tuple here. And what you can prove also is that this generalized random variable is just a precomposition of f and a. How we interpret this in terms of connecting fuzziness and random variables and so on. The idea is that you get some sort of like layering of the vagueness and uncertainty you have in your phenomenon, because f is gonna be like the classical random variable that keeps like the probabilistic uncertainty you have. A, it's an element of the algebra of Borel functions, meaning that A is a formula in a non-classical logic based on Lukasiewicz logic. So A takes somehow care of the vagueness that's appearing in your experiment. So this was more or less the model we landed on for this setting. And of course, this works also the other way around. So if I have any x defined in this way, then there exists a unique measurable function such that this x is induced by f. So there is a 1-1 correspondence between these generalized random variables and the actual random variables. But the information you get in addition is this sort of layering of the uncertainty phenomena that there are in your experiment. And again, we like this because it's algebraic. Again, we have a definition of a generalized random variable, which is fully inside the algebraic setting. It's an homomorphism in the variety. And as I said, f is a measurable function, but if on A, I put a state, a sigma state, then I just get a proper random variable, and you can forget about these few lines here. This is just the way you get the sigma algebra on X, and this is very standard. Essentially, you do the smallest sigma algebra that makes every function in A measurable. This is just these two lines. You build the smallest sigma algebra that makes every function in A measurable. Okay. Now, back on Rota's recap. The idea is that you could do algebras of some random variables already with Stone-Gelfand duality and Stone duality for Boolean algebras. You could do it, but you would just land on continuous random variables, on compact and Hausdorff extremely disconnected topological spaces. Now, Mundici proved that you can at least remove one condition and have just compact outdoor spaces using MV algebras, but you still have to do continuous random variables. So what we prove is that if we move from semi-simple MV algebras to this very complicated class of infinitary algebras, seems that we are like restricting the algebraic settings, making things more complicated, but actually, dually, we can take this class of sigma semi-simple algebras that are exactly measurable functions, and this is what we wanted. And at the same time, in this setting, we can also have a algebraic characterization of a generalization of the notion of random variables. So again, this was really nice. And then I'm gonna finish, but I just want to say, skip, that, where is the theorem? It's here. That actually, again, at some point, I had sigma states on slides. Another result we proved is that in this setting, so for sigma semi-simple algebras, sigma states are again coherent in the sense of the finetti. They are conditionally coherent. So we can expand the finetti setting in order to include conditional events, not just events. And you get, again, that states are coherent alla de finetti. So it all comes together very naturally, because it's a generalization of the setting, which seems to be rather complicated, but then eventually boils down to Borel measurable functions, which is not that bad if you want to deal with probability. And I'm gonna finish here. I'm gonna skip all these things. Thank you.
Coding here.